Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillah ar-Rahman ar-Rahim. Inshallah, today is the actual first lecture of the course. The last lecture was just an introduction to what big data is, and the orientation that we did in the first lecture. And I'm happy that you managed to stay in the course after what I said last time. This lecture is extremely important. Especially if you don't know anything about MapReduce. Because many of the lectures will depend on our understanding of this. So I hope that your mind is really fresh, you are ready to get into this very nice, very exciting realm, inshallah. Okay, so this lecture, inshallah, will be introduction to MapReduce. If we manage to go through everything that I am planning to, we can also start to get a quick introduction to Hadoop, but probably we will not be able to. But what is planned is that for the next lecture, inshallah, we will have an introduction to Hadoop. But this lecture will focus on MapReduce with the basic concepts of MapReduce. Okay, Bismillah. Last time we talked about why we should care about big data and what big data is. This, inshallah, lecture we will talk about how we can deal with big data. And the idea actually is very simple. When we get to tackle big data, we'll have to leverage a very known concept in computer science, which is divide and conquer. I am sure that you heard about this somewhere before, right? So what is divide and conquer? Yes, we have a big problem, we break it into smaller problems, then we solve each one separately, kind of independently, then we merge the solutions together somehow to get the solution of the bigger problem. Okay, so that's the main idea. So we have a piece of work. Okay, so let's say that this is our problem, but now we are talking about data, so that's why it's called work here. So we have large amount of data. We want to do something with it. So we will divide it into small pieces of data. And then for each piece, we will assign it to what we call a worker. So this is a machine or a processor or a core, some computing unit that will be responsible of processing this piece and producing something out of it. Okay, so this is analogous to the dividing the problem into subproblems and then getting the solution of each subproblem. Now what is remaining is to aggregate these small pieces into the final result. So it's that simple. Okay, so that's divide and conquer. And I think the concept you already have studied before. Now, in our context, when we have big data and our application is data intensive, we will see here from this picture that we'll have so many parallelization challenges. What do we mean by that? What are the problems here that we will face to parallelize such solution? First, before we talk about the challenges, what are some assumptions here? We assume that we are able to divide the data into pieces, and then we process each piece independently, separately, okay, independently. And when we do that, we produce some what we call intermediate output, which is ours here, okay, and then we combine at the end. So what are the challenges that we can face when we have a solution like that? Of course, this is a very abstract solution, but still we can think of what problems we can have when we have large data. Yes?
The first problem is assumption that the problem can be broken.
So how to break the data into pieces, this is one. What else? So that's a challenge.
How to know the place of each part.
Sorry?
How to know the place of each part.
How to locate each piece and maybe move it to the specific worker that will process it. Okay, what else? the dependency case, maybe sometimes we will need, some of the workers will need to share some of the data with other workers. How can we do that? Okay, what else? What if one of these workers is very slow and the others are much faster? Will that be a problem or not?
To the process to another
Move?
process.
We didn't talk about that yet, okay? But we're talking about the challenges here. If one of the workers is very slow, would that be a problem here or not? Yeah, because we will not be able to aggregate, we need the kind of synchronization here, right? We need a mechanism to synchronize the output somehow so that we can aggregate it, okay?
What will happen if one worker also fails?
Yes, what happens if one of the workers fail? If one of the workers fail here, then maybe the output will not be the output that we want. Okay, so many challenges here. Here are what I got. I think we got many of them, if not most. So how do we assign work units to workers? We get it. What if we have more? Oh, we didn't get that. What if we have more work units than workers? Maybe the workers that we have will not be able to, in parallel, to process all of this data. What would we do? That's a challenge that we need to overcome. What if some workers are slower? We say that. What if workers need to share partial results? We say that. How do I aggregate? We say that. How do we know all the workers have finished? That's kind of the synchronization problem that we talked about. What if workers die? We also get. Yes.
I thought that when we said the problem of breaking the data into pieces would address the issue, the number of workers.
Now, these are two problems. How to break the data? That's a problem, even if we have enough workers. And the other problem is, what if we don't have enough workers?
No, I thought that we would be thinking of the problem of breaking the data, the send in parallel with the workers would tend to break it into
But that might not be the best way to do it. Okay? It might not be the best way to do it. So that's why there are two issues here. Okay? Any questions about that? So it's very easy, right? All of these challenges are easy to overcome. They are not at least straightforward, right? So we need to think about all of these things when we have big data. Right. What is the common theme of all of these problems? There is a common theme here. Okay, think about these problems, okay, and what is common, and think about what is common about between them. All of them come from a specific common problem. Okay, so all of them are, of course, parallelization problem, but all of them are around what I think you studied before called concurrency, okay, and synchronization problems. So in concurrency, what do you mean by concurrency? We have multiple processors or workers, and they all compete for some shared resources. So we need to synchronize between them some way, okay? Some way we need to synchronize between them, okay? So that we can execute them in parallel, and then we get their output and produce the final output out of that. Okay? So there must be some communication between the workers, and because of the need in some applications to share some resources, we have to synchronize between them. So we need a synchronization mechanism. So that's common theme around these problems. And it is difficult to have a synchronization mechanism that will solve all of these problems. It's not impossible, but it is difficult as what you see here on the slide. So what is this? What is it called?
No signal.
Huh?
No signal.
No signal, but that no signal has a consequence. What is the name of that problem? Deadlock. Okay, I think you heard about it in operating systems, right? Deadlock. Everyone is waiting for the other. Okay, did you face this before, by the way? Here? Huh? No. Did you face this situation that you see in the slide? Okay.
Saudi Arabia.
In Egypt also, in Alexandria, for sure. that happens in front of my university, my college. that's always the case, and people get out and try to to solve this problem. So it's not easy. Okay, it's not easy. Right. So concurrency is difficult to reason about. We all know that. We all know that the topic of concurrency in operating systems is a hard topic. It's not easy. Okay. It's not easy to think how you can synchronize between multiple threads. We are always talking about threads in that sense, right? Threads of one machine. That's just to put you in context. The difficulty of that was when we were talking about just one machine. Here the scale is different because we are trying to synchronize between different machines, multiple machines. So it's difficult to reason about. Of course, at the scale of data centers, as we will see, it's even more difficult. In the presence of failures, it's even more difficult. Okay, many interacting services, it will be very difficult. And of course, not to mention debugging. Debugging in such environment will be a big headache. Okay, right. So what happened? So this problem is not new. This is known for a long time. Okay, and there was some solutions, but all of these solutions were what we call one-off solutions. Every group or every company has its own solution so that it can deal with this big data with maybe some of the customized system for them that can solve this problem. And so everyone wrote his or her own or its own dedicated library. And of course, this is a burden on the programmer because you have to keep track of all of these details even before solving your own your actual problem. And you have this big data because you are concerned about this big data because you want to do something useful with it. You have a specific problem. But now, instead of focusing only on how to solve your problem, now you will be focusing on so many low-level details like what we mentioned earlier. Okay? So that was the reality. So if you remember this is called, if you remember the computer architecture course, this is a mix of courses now. Right? If you remember, this is called von Neumann architecture. So this is one machine. Okay? And we had difficulty in thinking about concurrency and synchronization within that machine. Now we have something like this. So the idea here is that we cannot think of that, we will not be able to really reason while thinking that way, while thinking that we actually have so many machines like that and we have to synchronize between them. So that was not a good solution. Just the abstraction that we need to really keep track of all of these different computing units, how to synchronize between them, what if one failed, and all of the challenges that we mentioned. It's very difficult to reason about, in addition to your actual problem. Okay, so here is what we propose as a solution: that you think of the data center. And we will, of course, explain what we mean by data center. The center is just the cluster of machines that you would use. You think of it as as the computer, as one unit, okay? And you don't bother yourself with all of these details. If that happened, and all of these details are solved already for you, then you will be freed to actually think about how to solve your problem. your actual problem, your high-level problem of what to do with this data, not how to deal with these low-level networking and synchronization and concurrency problems. Okay? So that's the main abstraction here. So that's the right level of abstraction that I think is important here in order to deal with such a situation. Not to think about multiple computing entities as we saw. No, we think of the data center as just a computer, and we program that computer, and we are good in that, right? We used to program just one single machine very well, I assume, right? Now we want to think of all of this cluster of machines as just our computer. But of course, we need better programming models because it is still not one computing machine, right? Still, it is just an abstraction of all of these machines. So we need new programming models that will provide us with that abstraction, that will hide from us all of these details. So the idea is we want to hide system level details from the developers. So no more worry about race conditions, about concurrency, about locks, all of these nice things that you heard about in operating systems. And that will separate, as I mentioned earlier, it will separate the what from how. Why is that? How is how things are done actually at the low level. What is what you want to do? Okay, so you will focus on dealing with your data, not how to move the data and how to synchronize between the workers and how to cope with failures and all of that. You will not bother yourself with that because that will be already solved for you for once and for all. So you should not worry about that. So the execution framework, or what we call the runtime, will handle the actual execution of your programs. So you don't care about how things are done underneath, you will just care about your own programs. Okay? That's why we say that we'll separate the what, the what that is the application level, from the how that is done at the low level, at the system level. And that actually distinguishes between that course and distributed systems course. We not talk about here how things are actually done to solve all of these problems. We'll have an idea of how, very high level idea, but we'll not get into details of all of that. These details you can talk about in distributed systems courses. Okay? Any questions so far? Okay, good. So keep in mind this slogan, the data center is the computer. Now, what are the building blocks of a data center? Okay? I don't know have you ever seen a data center? Anyone of you? Or you saw it, of course. Okay, anyone else? You saw it in IT? Okay, very good. So what is this? No, it's not a rack. it's just a one server, it's one machine. Okay, so it's one machine. Okay, but it is inserted into the rack this way, but it's just one server. Okay, this is a rack. So the rack has multiple servers. Huh? A lot of fuses. A lot of use. What do you mean by that?
For example, this server you just showed is one rack has maybe 24 users.
Yeah, many, yeah.
So you can have 24 servers. U is a measure for the space.
Ah, okay. I'm not aware of that. Okay. Yeah, okay. But here the idea is the rack is a rack of servers. Okay, so each row here is one of these servers. Okay. Then what is the data center? Is a collection of these racks connected together. Okay, so that's the data center. They are connected, all the racks are connected through the cluster switch, and these are the server racks. Okay? So just to get an idea about the architecture of a data center. More into the components. So we have, this is the server, okay? Server might have multiple processors or cores, okay? Of course, all of them will share the memory, and they also share the disk, okay? And they have, of course, their own caches. Then we have the rack. So the rack has multiple servers, like what you see here, each with its own RAM and disk, and then the data center switch will connect all of these. Okay, and these are some numbers. I think these are like maybe 10 years old numbers, so don't really take this.
This is only for the sake of analogy.
Yes, sure. You're sure. So these are not up-to-date numbers, of course.
No, not numbers. I'm talking about the representation of.
Yeah, it's very, very, very general, yes.
It's much different how we implement it now when it comes to pooling of the resources. When you say data center is
Yes.
computer, today is much different than looking at data center as a set of
Racks.
with
Sure. Now, all of this.
It's for the sake of analogy. That's what I'm.
Yes, and all of this, we mention it now, right? But we don't care about it. That's the beauty of what we will learn here. We don't care about where and what at all. Okay? Everything will be transparent, not transparent, will be hidden from us, all of these details. But it is good that you understand it, because if you understand it, you can utilize the framework much better. Okay? Right. Here is some charts about the performance of these units. You will see, of course, as we move towards the right, you will see the local RAM, local disk. Of course, local disk has more capacity, okay, which is the size of the data that it can take. So always the disk, of course, is higher than the RAM, and of course, as we move towards the rack and the data center, the capacity increases. Now, how about the bandwidth? What is the bandwidth, by the way? Yeah, how much data I can transfer per time unit. Okay, so of course I can transfer data, or I can get data from, I can transfer data through memory much faster than a disk, and of course much faster within the same rack. It's much faster than getting it, or than the bandwidth through the entire data center. Okay. What else here? Latency. So what is latency?
Latency is delay.
Yeah, so it's the time to get something, to get some data from, for example, memory to the processor, from the disk to the processor. Okay? So that's the initial delay that you'll have to wait for until you get the first thing, and then you will get a chunk of data transferred. Okay? Type. This is a Google data center. This is the background of the first slide almost. So that's a Google data center. That's another one. You see how many.
Talking about basically, because the pooling of the resources is busy chain inside the rack. So when you look at the rack, you can say that it's not many servers in the rack, but the rack is the server itself. Because of the basic
You can think of it that way, but it is actually multiple servers or multiple machines.
Yeah, but some of these, because later on guys who made this for Google, they went out, they started a company called Nutanix. And they are building this hardware now, they are selling it commercially, where it doesn't have to be classical server, which means memory, processing power, and storage. You can have one rack storage, one rack.
We'll talk about that later. But we are talking here in context, in the context of this course or of the type of applications that we are talking about, this is not the case. So we'll talk about it, inshallah, today. Okay, but this is an actual data center. That's another from Facebook, just to give you an idea how these things look. I didn't actually see the data center here in the university. I would love to see it. And what is this? That's the cooling system. Yes, that's just the cooling system for the data center. Okay, it looks nice, but it's of course it's that complicated. That's another one for Google. You need, of course, for all of this, these machines, you need lots of power and cooling and ventilation.
That's actually the biggest problem.
Yes.
Power consumption is most dependent on the cooling.
Yes, there's lots of research, of course, on how to optimize power for data centers. That's a big research area. This is how the data center looks like from outside. Okay, so that's one of the data centers. These are kind of old numbers, but just to give you an idea. Okay, so the data centers mainly have commodity machines, and that's what we discussed last time, right? What do you mean by commodity machines? Didn't we mention that last time? Like home machines, like desktops, at the power of desktops or laptops. Let's say desktops. Okay, so the machines that normal people will buy or can buy, okay? Not powerful servers. And for Google, data centers, of course, are distributed around all the world. In 2007, which is 14 years ago, it was estimated that Google has 1 million servers. In total, 3 million processors or cores. It installs 100,000 servers each quarter at that time, which costs $200 to $250 million per year. And that was estimated, and this is the most important number in this slide. That was estimated to be 10% of the computing capacity of the entire world at just one company. Okay? I don't know what the number is now, but that's huge. Huh?
I think that Amazon would go
Maybe. Okay? But just to get you an idea that at the level of companies, they have that power to have some very good percentage of the entire computing capacity in the world. Okay, back to our slogan. The data center is the computer. Now we are ready, I think, to talk about MapReduce. Any questions up to this point? Questions? No questions? Okay. So, did I manage to show you how difficult the problem is? It is clear? Okay. Because that's important to know now, or inshallah later in this lecture, how beautiful is MapReduce, because it's a kind of very nice solution to this.
Even though if you work with it before, it's kind of, you forget what's the complexity behind it, what kind of issues you would
At some point, yeah, you will forget.
Data. I mean, long time ago, I remember when they just introduced parallel computing, when you had, as you said, custom solutions from Sun and others.
It's a headache. It's very hard. To get into that, you need to be very skillful. And not anyone can do it. But MapReduce made it for anyone to do it. That was the key point here. But of course, there are, as we will mention, there are some side effects. Okay, so what is MapReduce? What is MapReduce? So MapReduce is a distributed programming framework for processing large amount of data over a cluster of machines. So let's get through one by one. Distributed programming framework for processing data. What do you mean by distributed programming framework? Does that mean that we will code over different machines? And we'll write some code here and some code there, and that's distributed programming? Of course not. Okay, we'll write our program on one machine as we used to, but it will run over cluster of machines. Okay, so that code will be replicated to run over multiple machines. And of course, that will be supported by the framework, which is MapReduce.
Basically, it's what you mentioned in your previous slide. This is your execution framework.
Yes, that's yeah. But here okay. Well, we'll later in the lecture we'll say that MapReduce means multiple things. Okay, but here in that slide we mean the programming model itself. But of course, it has associated runtime or execution framework. And I don't think I need to explain anything about large amount of data. Okay, I think you now know what we mean by large amount of data, and over a cluster of machines. Okay, they don't have to be, by the way, in a data center. And you can install Hadoop, which is the open source implementation of MapReduce, over any group of machines. You just need them to be connected somehow, and you can install Hadoop on that. Okay, but all virtual machines, yes. Anything that you can do mostly with actual machines, you can visualize it. But doesn't have to be on a data center. That's the point that I want to say here. But of course, with really big data, data centers, of course, will be used. Okay, so that's the simple definition. So it's a model or a framework of programming that will allow the programmer, the normal programmer, to write code that will run over a cluster of machines to process large amount of data that is distributed over that cluster. Now, this is one of the most important slides in that lecture, which is about the big ideas about MapReduce, behind MapReduce. Okay, so we'll go through one by one. We'll try to understand as much as we can, and then the understanding, I assume, will be better when we talk about the details of MapReduce. But I want you to keep in mind these big ideas from the beginning. So the first one is scale out, not up. What do we mean by that? What do we mean by scaling out and scaling up?
You scale horizontally, you don't scale vertically, in the sense that you would rather distribute the work over the equal members of the cluster than increase the computing power of the
Yes. Yes, so scaling up means use more powerful machines. Yes, use supercomputers. And instead of 100 machine, no, just buy one supercomputer and that's it. Okay? Scaling out is distributing the work over commodity machines even, not any high power, high computing machines, just commodity machines. It turned out that, of course, scaling out is much more cost effective than scaling up. And we all know that when we go and try to buy even a laptop, or just single RAM, okay? If you double the size of the RAM, doesn't always double sometimes it's not just the double of the price, it's even more. Okay, so when you scale up, at that scale, the cost will be really, really high. But if you use just commodity machines, it will be much more cost effective. I think in the book it says something like on average like 41 to 45, something like that. I don't remember the exact number, but it's much more cost effective than scaling up, of course. Fine. This is one point. Another point is the performance is comparable. Of course, we cannot say that the performance of the commodity machines as a group will be exactly like the supercomputer one with the scaling up, but it is, for the data intensive applications that we are talking about, they are really comparable. So overall, this is a very good idea that will make this technology available to so many people, so many companies. Okay, you don't have to have really a fortune to run this kind of applications. Okay? So this is the first big idea. You should not spend your money on making your machines more powerful. Just collect more normal machines. Okay, so that's the first idea. The second one, move processing to the data. And I think you mentioned that before. Someone mentioned that, right? Move processing to the data. Did you mention that before? Okay, so what do you mean by that? Move processing to the data. We are used to the opposite probably, right? We usually move data to the processor, right? From memory, from disk, right? We always do that. We move data to the processor. We used to that concept of moving data from the data storage to the processor so that it is processed. The concept here is a bit different. We want to move processing to the data. What do we mean by that? What is the actual problem that will not allow us to do the normal thing, which is moving data to the processor? Yeah, let's think together. Forget about what is written here. Let's say that this says move data to the processors. Would that be problematic? Yes, we are talking about big data, right? We are not talking about very small data. We are talking about big data. But why is that a problem? Yes, of course it will take a lot of time because we are talking about a network here. It's cluster means there is a network, right? And with network, of course, there is latency. So that will not be a solution. It won't be a good solution to always move the data. So you have to optimize this part. So we will move processing to the data. Of course, we will not move the processor itself to where the data is, but what we mean here is that both are on the same machine. So we don't need to move data across the network. Okay, so moving here means across the network. We want to avoid that. So the data and the processors are co-located on the machines. They are not, as you mentioned earlier, that there is a storage area network that is separated from the processing units. Because in that case, we'll have to move the data across the two networks, and that will be very expensive in terms of time. Okay, so the idea here is that both processors and data are co-located in the same machines, so they are local. So the processor, of course, as much as we can, not always 100% will be done like that, but we will try to do that as much as possible. To do what? To process the data where it is located. And that's because the processors, the computing processors are co-located on the same machines with the disks, with the data. Okay? Is this clear? Because this is very important. Clear? Okay. So the third one, process data sequentially and avoid random access. Process data sequentially and avoid random access. Right. What does that mean? Let's go through an example to tell you what does that mean exactly. Yes. No, it's okay. Yes, to seek something, okay, and when in a random access, which means anywhere, okay, it will take time because of the latency. So here's a very nice example. Let's say that we have a 1 terabyte data with 100 byte records, and each record is 100 byte. Okay? And let's say that our task here is that we want to update only 1% of this record. Since we have 1 terabyte data, and each record has 100 bytes, so we have 10 to the power 8 records, okay, that we want to update. We actually have 10 to the power 10 records, and we just need to update just 1% of them. Okay, with me so far? Are you with me? Huh? Yeah. Okay. Fine. So that's what we want. Now let's assume two scenarios. The first one, we will do random access. Okay? Because the data is not, this 1% is not guaranteed to be all in one chunk in the data, right? It can be anywhere in the data. So we'll have to bring each one and update it. And let's assume that each update will take 30 milliseconds, because we have to seek to where the data is, we read it, and then we write it back. Okay, it will take about 30 milliseconds, let's assume that. So we'll need to do 10 to the power 8 updates. 10 to the power 8 times this 30 milliseconds, that will give us 35 days. Days to do that. Okay? Now, the other scenario might look very silly and maybe unfeasible, which is, let's rewrite all records. Let's read all records and write all of them sequentially. So we'll not seek 10 to the power 8 times. We'll just seek once and read sequentially and write sequentially. So we'll write even the records that didn't change, we'll write them back or ignore them, and that doesn't matter now for that, but let's assume even that we will write them back. But we will actually change only 10%. It will take just 5.6 hours. Where is the problem here? Why we got that much lower number, much faster time? Why it doesn't seem that we will get that here? Huh?
There is no return information in the operation, like in C.
Yes.
You go, is it true? No. Is it true? No. Is it true? Yes.
No. Okay, no. Let me explain that. In scenario 1, we don't seek for every record. We actually seek only for the 10 to the power 8 records here. Yani we know where they are.
All of them until you find them.
So you will seek for each one here. Yani in scenario 1, you seek for each one. This seek means latency. Okay? So it will, yeah.
The operation itself is trying to, even though you know where it is, in order
You have to seek to it. Yes.
When in scenario 2,
You just seek once in the beginning and you read everything. Yeah, you don't do random access. You don't get anywhere in the disk or memory. Of course, we are talking about disks here because we always assume that our data is on disk, by the way, because it's big data. It doesn't fit. Chunks of it will fit in memory, but they are mainly on disks. So, Oh, but not all of them, of course. Not the entire data. Not the entire data. Okay? But this is just an example, just to show you different. When we have specific application in mind, our design decisions might not look like justified in the beginning. Okay, so scenario 1, which is just random access as we usually do, it will take 35 days. But if we read the entire data sequential and write it back, it will just take 5.6 hours. So the lesson here is that we should avoid random seeks. Okay, did you understand this? Any questions about that?
Yeah. Again, I think this is valid about disk and memory because other interpretations that grew around Hadoop as open source,
like Spark. Yes. Yes. But that's if memory is large enough. Okay. But in Hadoop, you don't assume that, of course, the memory is large to the size of the data. Okay, so the data will reside on disk, and we will get whatever we need, okay, from the disk. Okay, so the main idea here is to avoid random seeks. Okay, still we didn't get to the programming model yet, but we are thinking about these big ideas that will affect the design decisions for the framework. Okay, so what are the big ideas so far? We discussed 3 of them. Scaling out, not up. Okay. Okay, this is the one that's on the slide. Okay, what was the second one? No, that's the third one. Avoid random seeks. What's the second one?
Move the processing to the data.
Yes, we move processing. We move processing to the data. Okay, we move. Yeah, I myself still think about it before I say it, because I used to move data to the processor, so you have to reverse it before you say it. Okay, so move processing to the data. So that were the 3 ideas so far. Question? No. Okay, I see something on your face. So that's
sometimes you try to answer something and you realize I didn't put the question or know the answer.
Okay, good. The fourth one, which we already discussed, is hiding system-level details from the developers. And this is extremely important because it allowed so many programmers to easily get into that field or that area or that kind of applications. Okay? If not, then really much fewer programmers will be able to do such things. But hiding these all system level details make it much easier for all of us. The last one is what we call seamless scalability. Okay, seamless scalability. First, what do we mean by scalability? When we say that this application is scalable, what do we mean by that? Ability to scale. What do you mean by that? Scalability is the ability to scale.
Consistency, while the data is coming big and big.
Okay, if you think about perfect scalability, when we double the data, the size of the data, what will happen to the processing time? It will double only, right? So linearly. Okay? If I increased for the same size of the data, if I double the machines, shouldn't be perfect scalability. It should be half, right? Because I now have double the computing power, so the time should be half. But that's perfect. That's the perfect scenario, of course. Okay, that's the perfect scenario. But believe it or not, MapReduce really was a very big step towards something like this. Okay, but what we mean here by seamless? When you use MapReduce, you don't care about how many machines you have. Okay, so your code, the same code, will run on 3 machines as it runs on 300 machines or 3,000 machines. You will not change anything in the code. Okay, so that's seamless to us, and the performance is really good. Adding also machines is seamless, and if you have a cluster, you start with a cluster with 10 machines, you add more machines, your code will not break. It shouldn't break. Okay? If you lose some of the machines, it won't also be affected. But of course, the time will change. Right? The processing time will change. But you don't need to change your program. Yes?
Your opinion is, in the past, when we had parallel computing, it was usually for custom application, custom
Yes.
made for
Very specialized people.
So we now say MapReduce, he opened this door, for many. But in essence, if you look at it, MapReduce is made for big data.
Yes.
Right? So it is specialized itself in the application. So it didn't revolutionize the parallel computing in the general sense.
It just made it much easier.
Made it much easier for big data applications.
Yes, of course.
Because when you look at it, still, if you have some special application that, you can call it virtualized layer, that execution framework that takes care of everything for you, it's only for big data. If you want to some other application, you will still need to build either data acquisition
Yes,
or you will need to program directly into the parallelized system. Right?
yes, and we will talk about whether MapReduce is good for all applications or not. Right, so the answer is, of course, not. Okay, but which type of applications we'll talk about, inshallah. Any other comments, ideas, concerns, questions, problems? Okay. Right. So these are the 5 big ideas. There's one more, by the way, in the textbook about failures. We will get to that, inshallah, also when we talk about the details. Okay, now, here is a very high level, you can think of it as an algorithm of processing large amount of data. So if I have large amount of data, here is one way of doing it. You iterate over a large number of records. You have large number of records already, so you will iterate over them. From each one, you will extract something. You will do the processing and you will extract something out of it, which we'll call it intermediate output. And then you will group these intermediate results somehow, some way. You will group it so that you can, in the next step, aggregate them based on your application, and then you write the output. Okay, very abstract way of looking at how you can process large amount of data. Okay, I think this is straightforward, right? Any question about this? Now, where is MapReduce? This is the map function, and this is the reduce function. So the map function will take one record and produce something out of it. What is that thing? Of course, it depends on what you want to do. Okay? So you as a programmer, you will need to provide that function. Because of course the framework doesn't know what you want to do with the data, right? But you know, this is what you want. This is the first step of what you want from the data, is to process every single record in your data. Okay?
I think I also read the textbook copies the functional programming rules where you have not and fold.
In the function programming, yes. Yes, it is not new idea, of course, okay? But it put it in a nice framework that solves all these problems. Okay, so that's the map function that the programmer will need to write. There is also another function that the programmer will need to provide, which is called reduce function. The reduce function, the idea of the reduce function is to aggregate some of the intermediate results to produce the final output. We didn't, of course, talk about the details here, but this is just the big picture. So the programmer will only provide these two operations, map and reduce. You can think of it as operations. Map will operate on every record, and reduce will operate on some part of the intermediate results to aggregate them in some way and produce the final output. Yes. About the other steps, right? Because we said that we have 5 steps here. The third one, okay. What is your question? Okay, very good. And we said that the key idea here that MapReduce provide these abstractions for these two operations, which means that the developer or the programmer, can you be with us, please? Which means that the developer or the programmer will have to provide code for these two functions. Now, how about that step that is in the middle, the group intermediate results? That will be done automatically for you. You don't need to provide any code for that. But you didn't ask me also about the first one. Yes. It will be done also by the framework for you. You should not care about going through all the records. Your function will be called for all the records automatically for you. So all of what you need for now, okay, we'll add some more details later in this lecture, but for now, the minimum that the programmer will have to provide is these two functions. The map function that will take one record only and produce something of interest of it, and the reduce function that will aggregate some of the intermediate results to produce some part of the final output. Yes?
How about data that will be divided in functions? Have data that will be extracted through MapReduce.
Yes.
So, program will be dividing data.
Yes, the dividing the data. Of course, we'll talk about some things that the programmer also has to do, and the programmer also has to define something about the structure of the data that we'll talk about, I think, in a couple of slides. But other than that, the framework will handle how the data will be split and how the data will be distributed over the workers or the mappers or reducers, the machines that will process the data. Okay? Stay tuned. We'll have more details. Yes.
Is it always, I mean, also understand this is it always the framework does this? Always.
Believe me.
You never need to tell it how to
Believe me.
group it.
Believe me. Yes. Yes. Wallahi, even this is called shuffling. Yes, we'll get to that. Yes, shuffling is completely automatic, and you will know why. And it doesn't need your code because it's a very well-defined operation. Okay, and that's the reason. You don't need. It is well-defined operation. You don't need to do anything. If you adhere to the structure of your code, to the structure of the programming model of how map is called, I mean the signature of the map function and the signature of the reduce function, everything will be seamless for you. Okay? More details later, but we'll get into it step by step. First, the key idea here is that MapReduce framework will provide to you as a programmer an abstraction, function abstraction of these two operations, map and reduce, which means that you will have to write a map function and you will have to write a reduce function. And these two functions will actually define what you want to do with the data, as you will see very soon. Okay. Should we stop here? Because this is a very important slide. I don't want to interrupt it. This is really the most important slide in this lecture. So I think we should start with it in the second part. So let's stop here and come back at 6:20.